here's the setup. So, Dr. Dorkus Malorkus is rescuing Princess Leia from Darth Vader. And what he has to do is he has to swing from here, this ledge, to a ledge over here that you don't see, over an inexplicable chasm. And so, what we have to figure out is a couple of things. We need to figure out the tension in this cable, we have to figure out the stress in this wire, and the stress in that wire. And so, we also have an extra credit problem, and that is who is Dr. Dorkus Malorkus, which we will get to at the very end of this segment. Alright, so, some information you're going to need to know. The cross-sectional area of the wires is the same, and it is 0.007854 square meters. This wire is made of tungsten, and it has a modulus of 375 gigapascals. This one is made of steel. It has a modulus of 200 gigapascals. This is the inexplicable chasm. This is Dr. Dorkus Malorkus. This is Princess Leia. Some information about them. There's a lot of information. They have a mass of 122.3 kilograms, so their weight is 1,200 newtons. They're traveling at a speed here at the bottom of this loop, I guess, that they're swinging on at 2 meters per second. The bar here is 10 meters long, and we're going to assume that it is a magic bar that doesn't deform. The bar is 10 meters long. This first wire is located at x equals 2 meters, second wire at 8 meters, and then there's 2 meters between the second wire and where they're hanging off. So, first thing we have to do is we have to find T. So where we're going to find T is you add up the forces in the y direction, which is mg plus the force of the centripetal stuff that's going on. And so the way to figure that out, centripetal force is mass times the centripetal acceleration. Centripetal acceleration we can all recall from whatever dynamics was we took. V squared over r, so you have 2 squared over 15. This is 15 meters long. Gives us 4 for 15. Great, wonderful. We put it into this. We get 32.62 newtons of centripetal force. We add that to this to sum the total force. We find that the tension in this wire that they're hanging from is 1,232.62 newtons. Okay, now we go over here. Now that we know tension in that cable, we need to find out the stresses in the wires that are pulling the bar up. And to do that, we have to find the tensions in those wires. And so we're going to start by summing the moments around the joint of the wall. Okay, so we sum this up, 0. We have the first tension times the first distance, the second tension times second distance, and then tension that we just calculated times total distance to the bar, x3. But we need more info. We have to go deeper. And so what we're going to do is we're going to find geometric relationship between the dB and dC, the amount that they go down because of the weight of Dorkus Malorkus and Leia. And so dB here, you do some geometry, it's this distance times sine of theta, because it's that distance, times this theta that they make here, so that's theta, there you go. Do that, do the same thing for dC, they both have the sine theta. Solve them in terms of sine theta, and then you can relate them using this relationship, which is good. It is dB equals x2 over, well, dB times x2 over x1 equals dC. So, we'll go over here. Next step, what we have to do is we have to solve for the tensions. And so we use the deformation equation that we got from the book. dB equals, the form is PL over EA, so we've got T1 times 0.7h, and that length is the length of the wire that they're hanging from, and it is 70 meters long, because, you know, the future. So you've got that divided by E1 times A. Same deal for DC. You solve it like that. Solve them both for the tension. So you've got tension 1 equals dB E1A over 0.7h. Then you've got T2 equals DC E2A over h. Wonderful. What you can do with this one is you can solve this one in terms of dB, which is good. So that simplifies it. And so we have dB from what we had over there. I'll demonstrate that one. dB times x2 over x1 equals dC. Put it in there. You get dB times E2A over h times x2 over x1. Okay. So, we're going to solve for dB now. With this equation, which is the moment equation. And this has everything in it that we know and we can find out, so that's good. So I'll come over here, And we're going to go ahead and start solving these for numerical answers because it gets really nasty to put this in some other stuff. So you solve that and you get a tiny amount because it's an incredibly strong tungsten wire. And you can use the relationship that we had earlier, dB times x2 over x1 equals dc. So you do that, and that equals that many meters, 0.000024 meters. So not much deformation going on there because they're pretty light and it's pretty strong wire. So we've got the deformations. Now we need to find the stresses. We put these back into the form for the tensions. So we put that there, and we know that the stress is tension divided by the area, force over area. So if we do that, it's this divided by A, and this divided by A. So the A's cancel out, and you get dB E1 over 0.7H up here, and you get 31.5 kilopascals. And for the second wire, you get 47.1 kilopascals. And so that is how you solve that statically indeterminate problem. And for the extra credit, Dr. Dorkus Malorkus is our beloved Henrik von Langerich.